History of Vector Analysis, Episode 9, Hamilton's Scalars and Vectors. You are here. Hey, it's old Doc Oler. Before we get started, I want to note that I chose the title for this episode carefully. This episode is about Hamilton's scalars and vectors, which are the ancestors of our scalars and vectors, but differ in some fundamentally important ways. We're not there yet. In the previous episode, we discussed Hamilton's discovery, that was his view, of quaternions in 1843 and his work on them for the next decade, culminating in his massive Lectures on Quaternions, an almost unreadable mathematical tome laced to the gills with metaphysics. There were, however, some gems embedded in this matrix. The first of these that I will discuss is insight into the behavior and utility of a subset of quaternions whose real terms were zero and thus contained only the three imaginary terms. Let us consider two quaternions, let's call them Q01 and Q02, both defined with the real components set equal to zero. I want to clearly state that this is my terminology for these zero real quaternions and is not used anywhere else. Hamilton himself did not assign a verbal name to these things, so I just made this up for clarity. Don't use it anywhere else because no one will know what you're talking about. All right, what happens when you multiply two zero real quaternions? Let's go through the math. The steps are the same as always. First, you multiply out the terms, which because of the zeros will yield only 9 terms instead of the 16. Okay, you evaluate the IJK coefficients and you group by the coefficients. You see that the 9 terms are grouped as follows. There's 3 real and 2i, 2j, and 2k. The first thing to note, okay, is what you do not get. You do not get another quaternion whose real component equals 0. When you multiply Q01 by Q02, you get an I squared, a j squared, and a k squared term, all of which are real, and they are shown here, okay? Note that they are all negative. The second thing to notice is that for the IJK terms, one term within each set of parentheses is always positive, and one term is always negative. This is due explicitly to Hamilton's cyclic and anti-cyclic multiplication rules for the IJKs. Starting with these special case zero real quaternions, Hamilton takes great interest in their non-zero real products. In particular, he considers the real terms of the product as distinct from the 3 IJK terms, the imaginary terms of the product, to the point where he will coin specific names for them. I note in passing that he coined dozens of specific names for various types or parts of quaternions in his lectures, so this by itself is not as meaningful as it might sound. Mixing some of my own terminology with Hamilton's, I'm going to write Q01 times Q02 as capital Q, which is a genuine Hamilton term. In an 1846 paper, Hamilton introduces the term scalar to represent the real part of capital Q and vector for the imaginary parts. In his paper, he writes, I have been induced to call the trinomial expression itself, as well as the line it represents, a vector. A quaternion may thus be said to consist generally of a real part and a vector. And then elsewhere, the algebraically real part may receive all the values contained on one scale from negative to positive infinity. We shall call it, therefore, the scalar part, or simply the scalar of the quaternion. He then goes on to express his capital Q in terms of the sum of the scalar and vector components, which he writes as scalar Q plus vector Q, or S dot Q plus V dot Q, or just SQ plus VQ. How much of this is due to his metaphysical interest in the algebra of pure time and the 3 real dimensions, I don't know, but I suspect that it was probably some. Okay, was Hamilton really the first to use these terms? Crow writes, from the above quotations, it may be inferred that it was Hamilton who introduced the term scalar and also the term vector in its precise mathematical sense, although the similar term radius vector had been in use for many years before. Hamilton writes capital Q as the sum S dot Q and V dot Q. I want to reiterate that capital Q is not just any quaternion. It explicitly refers to those quaternions that are the product of two zero real quaternions. With the benefit of 2020 hindsight, we can see that the scalar part of this special quaternion S.Q is -1 times the sum of the diagonals, which we can further recognize as strongly resembling the dot product of two modern vectors containing the components b, c, and d. Similarly, we can see that v.q is very similar to what we today call the cross product of the two vectors. But be careful, these two sets are not the same. In Hamilton's S.Q and v.q, the squares of I, j, and k are all equal to -1. This is not the case with modern vector analysis. Further, a bit of foreshadowing on how challenging it will be to transition from Hamilton's vectors to modern vectors. Note that the sum of SQ and VQ, like all quaternions, follows the associative law of multiplication. But the components S.Q and V.Q individually do not. Here is a second gem buried deep in Hamilton's lectures. It involves the math associated with differentiating quaternions. His approach started out the same way as differentiating complex numbers, but evolved into something else. In consideration of the vector part of the quaternion by itself, Hamilton proposed a new operator, which he wrote as this sideways triangle, which is equal to I ddx plus j ddy plus k ddz. Note that this is analogous to the zero real quaternions that we just discussed. If he assigned a name to this operator, it has been lost to history. I retain the colors here to reflect that Hamilton's ijk are different than the ijk we associate with the del operator today. His are imaginary, ours are real. Okay, as is common in calculus, he also needed an expression for the second derivative, or the square of this operator. Let's run through the math, because that's what we do here at Old Doc Oler's home for troubled physics majors. If the sideways triangle is this, then the sideways triangle squared is this. Okay, as usual, we multiply it out, getting 9 terms. We evaluate the ijk's in the usual way. Note that for every cyclic ijk term, there is also an anticyclic ji term. Then we group them by type. As with the zero real quaternion multiplication that we did earlier, we get 3 real terms and a pair each of I, j, and k terms. In each case, one of each pair is positive and one pair is negative. However, unlike the case with multiplication, we have an identity that we can draw on. We know from calculus that d squared dx dy is always equal to d squared dy dx. So all of the ijk terms cancel each other out, leaving us with this sideways triangle squared, this, which is just the real part. Hamilton, being brilliant, no doubt instantly recognized the square of his operator was almost identical to what we today call the Laplacian. The Laplacian is named for the great French mathematician Pierre-Simon Laplace, who developed the operator that now bears his name in his great work on celestial mechanics. Laplace wrote his operator as a regular triangle. Again, if he had a verbal name for it, it has been lost to history, and it seems highly probable that Hamilton's use of the sideways triangle was an homage to Laplace. Some would go on to refer to Hamilton's operator as the square root of Laplace's operator, but of course there's that pesky minus sign that must be considered due to the fact that Hamilton's I squared is equal to -1. To summarize, Hamilton invented a version of the scalar and vector concept, although not quite in the form that we use today. As we will see, James Clerk Maxwell found that the true power of quaternions, which he tried to apply to his theory of electricity and magnetism, was in the del operator. This too was invented by Hamilton, albeit in a different form, but he did not develop it further. That task would be left for a man named Peter Guthrie Tait, whom we'll meet in a couple of episodes. In the next episode, I'm going to take another short break from the historical narrative and talk about one of the ways in which quaternions are used today in digital navigation systems and in software. How quaternions model rotations in 3D space. See you then.